Welcome back, and it's my pleasure to announce that the next talk will be given by Pietro Longhi from Uppsala University, and he will talk about Quiver structures of knot invariants, open strings, and recursion.
Okay, thank you very much, and thank you for the invitation. This talk is based on joint works with Pietro here and with Tobias Ekholm from a few years back. But also the second half of the talk will be based on some upcoming work with Tobias and a student, Lucas Nakamura. And so these projects grew out of our attempts to understand the relation between knots and quivers that already was mentioned earlier today, and in particular to understand what this relation has to tell us about certain physical settings, namely topological strings. So my plan will be to start by reviewing the motivations and the goals of our works, and after that I'm going to review a little bit how the two aspects of the knot-quiver correspondence arise in physics in a context that is known as M-theory. And having set the stage, I will then explain how we think about the knot-quiver correspondence in the context of M-theory, namely as telling us something about how fundamental objects in M-theory, called M2 branes, interact among each other in a way that's encoded by quivers, and how this interplays with the integrality structures in knot invariants that we've seen in the previous talk. And then in the last part of the talk, I will give you an overview of the upcoming work, where we place this into a broader context, and we lift what we have known for some time now about knots and quivers in this M-theory context, and we lift it to higher rank quantum curves and the notion of skein-valued quivers. Okay, so just a brief recap on the knot-quiver correspondence. So a quiver for me today will be a symmetric quiver, which is an unoriented graph with adiacioncy encoded by a symmetric matrix. And well, given such an object in mathematics, one can study its representation theory. And without going into the details, the main output of that branch of mathematics that we're going to need is this generating series called the generating series of motivic Donldson-Thomas invariants. So this is a function of formal variables associated to the vertices, and then it's a function of a variable q that depends on the adiacioncy matrix of the quiver. So the knot-quiver correspondence is the observation that sometimes you take such a quiver and you take its partition function, and if you specialize the formal variables as certain powers of a, q, and x, then after you reorganize the series as powers of x, the coefficients turn out to be knot invariants. And for that quiver, the knot invariants are the reduced HOMFLY-PT polynomials of the trifold knot, colored by symmetric partitions. So this goes back to work of Kucharski, Reineke, Stosic, and Sukovsky from 2017, but it's been now generalized to many families of knots, including torus knots, twist knots, two-bridge, double twist, and so on. And so it's a very general statement, it appears, that there is a quiver with a given adiacioncy matrix, Cij, and certain integers, ai, qi, such that when you specialize the partition function, that is, you specialize the variables to these powers of a, q, and x, what you recover is the generating function of HOMFLY-PT for some knot, colored by symmetric partitions. Now, one reason why this is very interesting to me is that as mathematical subjects, knots and quivers appear to be very, very different, but in physics, they're known to arise in the same context. They both arise in the context of string theory. So of course, knots came up a long time ago in work of Witten on Chern-Simons theory, and quivers also came up in sometime in the 90s in the description of the world volume dynamics of D branes. So what we wanted to do then, when we started these projects, was to understand whether this connection through physics between knots and quivers could help us shed some light on the knot-quiver correspondence. So in particular, one can be very precise and ask, how do you relate the adiationcy matrix or these numbers ai, qi to the knot? Also, is the knot-quiver correspondence valid for all knots? Is it one-to-one? And conversely, do you learn something new about physics from this correspondence? Of course, the answer is that we now know the answers for all these questions to some extent, and we're going to see later in the talk. So, to tell you how knots and quivers arise in M-theory, what I'm going to do is I'm going to introduce a bit of geometry that was already touched upon in the previous talk. So let me very briefly go through this. So given a knot in the 3-sphere, what we're going to do is we're going to embed this into T star S3. And then, given the knot, what we can do is we can build a Lagrangian in T star S3 called the conormal Lagrangian, which is the family of cotangent planes that is annihilated by the tangent vector of the knot. So this gives a Lagrangian L that intersects the zero section along the knot. And topologically, L is a solid torus. It's S1 times R2. It's a family of planes fibered over K. To introduce physics, what we're going to study is the A model on T star S3. This was studied by Witten a long time ago. And what Witten argued is that if you consider topological strings in T star S3 with n branes on the zero section, the world volume dynamics on S3 is given by a UN Chern-Simons theory. And if you're a mathematician and you're not familiar with these words, you can think of it as a theory of flat connections. And likewise, if you have, say, a single brane on L, that means you're going to have a U1 Chern-Simons theory on L. And these theories, they really come from strings or maps whose endpoints lie on S3 in the case of the UN theory, or the endpoints lie on L in the case of the U1 theory. But now when you have branes both on L and S3, what's going to happen is that you can also have strings that have one endpoint on S3 and one endpoint on L, and from the viewpoint of the dynamics on these branes, these will give rise to charged particles or charged fields which couple to the connections on S3 and on L. So these are called bifundamental fields. And as we've heard in the previous talk, they give rise to a contribution to the partition function that was computed by Auguri and Vafa. And this contribution is a function of U and X, where U is the holonomy in the UN Chern-Simons theory on S3, and X is the U1 holonomy on L. Now, computing the partition function of the theory on the 3-sphere has been shown by Labastide and Marigno to compute generating series of HOMFLY-PT polynomials. In this case, they're colored by symmetric partitions. So of course, this is exactly what we've seen appearing in the knot-quiver correspondence. And to identify this partition function with polynomials, one has to adopt this identification of variables. So GS is the string coupling. It's related to parameter Q appearing in the HOMFLY-PT. And the variable A is related to the rank of the gauge group, Q to the n. So what we're interested in is actually the large n limit. And what happens when you take large n is you have infinitely many branes wrapping the S3. And so it's been argued that when you send n to infinity, T star S3 gets replaced by the resolved conical. So one way to think about it is that when you have infinitely many branes, the energy per unit volume on S3 diverges. And so what you do is you create some kind of black hole. And the S3 shrinks away, and so strings cannot end on it anymore. And so you go from a theory of open strings with boundaries on a street to closed strings with no boundary. And this hypothesis was made by Gopakumar and Bafa, who verified it by showing that the partition function of Chern-Simons at large n agrees with the closed string partition function in the result conifold. Now, this story is without knots, but as I said, we're going to be interested in the case where we have an additional brane on L that intersects S3 along the knot, and one can introduce that through the transition by first shifting off the zero section. This gives rise to strings that stretch between L and S3 with some finite area, and then in the large n limit, these annuli, they become open strings which only have boundaries on L. Okay? So it's a very brief review of something that was already mentioned in the previous talk, but the main point for the purpose of this talk is that this is a sequence of dualities that implies a relation between the generating function of HOMFLY-PT polynomials, colored by, say, symmetric partitions for now, and a certain enumerative problem, which is counting open Gromov-Witten invariants or open topological string partition function in the result conifold with the Lagrangian brane. Now, this partition function is exactly the generating series that appears in the knot-quiver correspondence. So the knot-quiver correspondence says that the open string partition function is described by Quiver, and one can take this to mean that quivers really describe not so much knot invariants, but rather open strings ending on knot conormal branes. So this is the viewpoint that was already taken in the original papers. We studied this in some detail, and it's been expanded also in other contexts beyond knots. And to go in detail about this, that's what we're going to do next. Let's start from a very natural point of view, which is the genus expansion. So when the string coupling is small, the open string partition function is dominated by genus zero curve. So it's dominated to leading order by the disk potential. And it's been known for some time that the disk potential is organized according to an integral structure. Namely, one can write down the disk potential as a series of, well, powers of a and x. And if you reorganize these into dilogarithms, then the coefficients turn out to be integers, which are certain combinations of LMOV invariants. And in physics, we understand the origin of these integers as coming from M theory. So roughly speaking, Nij here count supersymmetric states of M2 branes, where I and J label the relative homology class of the M2 brane. So you should think of these as M2 branes, or some objects wrapping holomorphic disks, wrapping a number of times around the P1 and with a certain winding number around the Lagrangian. Now, we're working at weak string coupling right now, and this is a nice limit because in this limit, you can think of the brane as a geometric object. So the brane is defined by a special Lagrangian. That's the knot conormal, or well, certain deformation of that after the transition. And then there is the data of an abelian local system on the Lagrangian. And the moduli space of this geometric data is parameterized by two complex numbers, x and y, that you can think of as complexified holonomies for the local system on the boundary torus. So remember, L is a solid torus. It has a boundary. And x and y are the longitude and the meridian on the boundary. So in physics, when you want to study the dynamics of a system, you start from the phase space. So the phase space will be C star times C star. And then you need an action. And for this brane, the action has contribution from the local degrees of freedom, which is the constant maps. And that is the Chern-Simons action for the U1 theory, according to work of Whitman. And then there's the non-local degrees of freedom, which are the instanton corrections, which are the holomorphic disks at weak string coupling. So this is the action that describes the dynamics of the brane in the limit of GS goes to 0. And if you want to study stable configurations, then you have to minimize the action that leads to this equation. And this equation actually can be written as a polynomial equation in variable x and y. And this is known as the augmentation curve of the knot. So it turns out that what we've done so far is we've studied the dynamics of a brane. We've written down the equations for, well, the solution to the equations of motion. So this is the moduli space of stable configurations, but it turns out, according to work of Aganagi, Ekholm, and Gembaffa, that the same polynomial arises in another branch of mathematics, which we'll come back to, in the context of knot contact homology. And in that context, it's known as the augmentation curve. But in physics, this is the moduli space of our brane. Okay, so we've done this exercise with the open string partition function. We've said that if we take GS to 0, then that's nice because we get a geometric description of strings and branes. But now let's see what this means for the knot-quiver correspondence. So we know that the open string partition function should coincide with the quiver partition function. And one may expect that if you take the same limit on the quiver, you may get some geometric interpretation of Q. That's indeed the case. You have to take such a limit, but in a slightly non-trivial way. So the idea goes back to Fujigukov and Sukovsky to take a scaling limit where Q to the D, so this is the quiver partition function, you have some summation over D, and what you want to do is you want to say that Q to the D scales to a continuous variable so that the sum becomes an integral. And if you take the scaling limit, what you find is that the integrand is actually very nice. So it's a simple function, well, relatively simple, where you have a finite number of dilogarithms, one for each vertex of the quiver. You have some bilinear form in the variables associated to the nodes, and then you have some coupling to the variables x. So we're going to think about what this is telling us. But the first thing to realize is that this is the quiver partition function. In the knot-quiver correspondence, it's identified with the open string partition function. And we said that the leading order of that was the disk potential. So it follows immediately that this expression here, W tilde, is nothing but the Legendre transform of the disk potential. Okay? Now, I told you that the disk potential was organized by some integral structure encoded by certain integers, Nij. But in the case of the disk potential, we have infinitely many integers, and they do not have an apparent structure. In contrast, W tilde has finitely many dilogarithms. So we can think of these as M2 branes, just like we did for the disk potential. And the integers in front of these are all 1. So there's finitely many, and they're all 1. There's 1 for each vertex of the quiver. The trade-off is that in W tilde, you don't just have these Li2, you also have this bilinear form in the y variables, and you have these other couplings. And the idea, which I'll make precise in a moment, is that somehow these are a finite number of M2 branes that talk to each other in a way that's encoded by the integral that performs the Legendre transform for you, and the interactions are mediated by this bilinear form. So to understand what I mean by that, let's do some simple computations. So remember that by definition of Legendre transform, we're looking at two functions that have the same critical point set. And in the case of the disk potential, the critical manifold was the augmentation curve. In the case of W tilde, well, it's very easy to compute the critical manifold. You extremize with respect to the integration variables. And what you find is a set of equations that looks very simple, and it's kind of universal. So this is the same equation for all variables. And to understand the content of this equation, observe that if you have a potential with a single dilogarithm, so a single M2 brane, then the resulting moduli space, the resulting critical point set, would be 1 minus y minus x. So this is almost what these look like, except that here x is corrected by yj to the cij, if you forget about the sign. So what does that mean? The interpretation is that there are basic disks. There is one for each vertex of the quiver. And each of these basic disks has a boundary on our Lagrangian where the xi and the yi are local holonomies. So xi are the longitudes and yi's are the meridians, just like in this example. But then what happens is that if disk I links with disk j, then its longitudinal holonomy gets corrected by the meridian of disk j. So it picks up a shift. Instead of xi, it is xi yj to the cij. And so that tells you that these numbers cij should be linking numbers of the basic disks. So that's the interpretation. So to recap, what this exercise suggests is that, at least in genus 0, we're still working at weak string coupling. It suggests that you should think of the quiver as describing a finite set of basic disks ending on the Lagrangian. And the boundaries of these disks, they link with each other in a way that's described by the quiver radiation symmetrics. And somehow the spectrum of all NMOV invariants is generated by these interactions. So the first question is whether this hypothesis is still true when you go to higher genus. So at finite string coupling, there's no simple geometric description like the one that we've been discussing. What happens instead is that the classical picture of the brane is replaced by a quantum state, Z open, in a vector space associated to the boundary of the Lagrangian. And as in quantum mechanics, one can write down a wave function for this state that corresponds, in this case, to the open string partition function. And it's been known for some time that this wave function obeys a Q-difference equation that arises by quantizing the augmentation curve. Okay? So the question is whether this kind of structure can also be seen as compatible with the quiver description that I gave you. So the idea is that the quiver partition function can also be regarded as a wave function, except that now what you have to do is you take your Lagrangian and you have this finite set of basic disks, you have the boundaries, and you cut out some tubular neighborhoods around the boundaries. What that gives you is a three-manifold, which is a solid torus with many torus boundaries carved out inside. And if you do Chern-Simons theory on that three-manifold, you get a Hilbert space, which is associated with these torus boundaries. And so the partition function of the quiver should be thought of as a wave function in that space. So the path integral will define a quantum state, and one can show that this quantum state, or rather the wave function for the quantum state, is in fact annihilated by a quantization of the AI polynomials that I've shown you earlier, where we promote the xi and the yi to operators valued in a quantum torus algebra. And so this fact can be taken as indication that the quiver picture with finitely many basic disks with linking numbers continues to hold also at finite string coupling. Okay, so I gave you so far some interpretation for what the quiver is describing in terms of geometry and then in terms of some quantization of that geometry. Now, what I'd like to explain is how, in practice, this finite set of basic disks actually ends up generating the whole spectrum of holomorphic curves. So, going back to the open string partition function, the statement of integrality of LM of invariance can be expressed as the statement that the partition function factorizes as a product of a certain function psi q, it's a q-pokammer essentially, where the exponents are all integers. Now, in M theory, we think of those integers as counting certain states in a Hilbert space. And this is the Hilbert space associated to M2 branes. And there's infinitely many such integers in general for the open string partition function. On the other hand, when we have a quiver, we've said that there's finitely many M2 branes. There's one for each node of the quiver. So the question is, how is the entire spectrum of LM of invariance generated by the finitely many M2s that are encoded by the quiver? And the idea is that these M2 branes, they have some boundaries that end on the Lagrangian. So the Lagrangian itself is a dynamical object. I told you in the classical picture there was a flat connection. In the quantum story there's more degrees of freedom, but the point is there's a theory that lives on the brane that mediates the interactions between the M2s. And to model this, what one can do is one can promote these operators, these factors to operators, where we replace the holonomy variables with quantum holonomies. And these will be valued in a quantum torus algebra because we're doing a U1 Chern-Simons theory on the brane. In fact, I also told you that basic disks are mutually linking, so you should correct these quantum holonomies by the linking numbers. So xi goes to xi times yj to the cij. And the moment you do that, you get some quantum holonomy operators that do not commute. So you're going to get some interesting interactions among these M2 branes. And in fact, one can show that if you do that, so if you introduce these corrected quantum holonomies, you can in fact write down the full quiver partition function as a finite product of factors corresponding to M2 branes. So there's one factor for each vertex of the quiver, and they talk to each other through the fact that these variables do not commute. Rather, they have some interesting algebra that reflects the linking matrix. So what this equation does is it makes it absolutely manifest that at the quantum level, the quiver partition function is written as contributions from finitely many M2 branes that interact through a quantum torus algebra. Now, that's all fine. If you just want to get the quiver partition function, you can do that. You can show that this indeed works. But then there's one further question, which is, what about the integrality structure? So what I've told you is that there's an equivalence of two functions, which are, if you wish, power series in X. But there's also a fact that somehow here we start with a product of quantum operators, which are written in terms of this psi function, the q-pokammer. And the exponents are all 1. And at the end of the day, what you get is a quiver partition function, which is equal to the open string which is also a product of psi's with integer powers. So what seems to be the case is that somehow the algebra, this quantum torus algebra of x and y variables, lifts to an algebra of psi operators. So there's some kind of algebra of basic holomorphic disks that preserves the integrality structure. And the basic instance of this is the following. So if you take two basic disks that link once, then you would expect that if you try and unlink them, like I did here, then you can do that. You get two unlinked disks, and the price you have to pay is that you would have to create a bound state by skein relation, right? So if you translate this expectation into quivers, what you would expect is that you would have a quiver with two basic disks, so two nodes. There's a unit of linking, so there's a link between the nodes. And after you do this move, you get the same two nodes, do not link anymore, but then you created a new disk, so a new node in the quiver which self-links. And in fact, this expectation holds precisely if you postulate that the holonomy of the bound state is the product of holonomies of the two initial disks. There's a q to the minus 1 coming from this self-loop. And one can show that indeed, with this identification, these two quivers have the same partition function. So this fact that I just showed you is actually an instance of a well-known identity due to Fadeev and Kashar. It's the pentagon identity. And the reason why this holds is precisely because the variables, the quantum holonomies, have an algebra that's reflecting the linking matrix of the quiver. And this operation is actually quite general. It generalizes to arbitrary quivers where you have a set of nodes and you can remove a unit of linking between two of them. So k goes to k minus 1, and the price you have to pay is you create a bound state node, which will then link with everybody else in a way that's consistent with the geometric picture. So in this way, you can start from a quiver, you can start unlinking, and you create a new quiver with more nodes. And you can, in fact, generate the entire spectrum of bound states in this way. So there's many more things to say that we've explored in the paper, and they've been explored in other works. But the main upshot from this discussion is that we learn right away that the knot-quiver correspondence is not one-to-one, but there are minimal choices for the quiver. So there are quivers with a minimal number of nodes. And from a physics perspective, this kind of relations is interesting because, well, there's a construction that associates certain quantum field theories to these quivers. So these will be 3D n equal 2 QFTs, geometrically engineered by the Lagrangian, whose vortex partition function is known to agree with the quiver partition function. And the quiver encodes the structure of these QFTs, and when you have two equivalent quivers, what you get is a duality, in the sense you have two different quantum field theories that happen to have the same properties, or at least the same spectrum of vortices. And this is interesting, but in fact, it also gives a strong consistency check, because one can show that this kind of relation from the viewpoint of quantum field theory is consistent with previously known dualities, such as particle vortex and SQED XYZ. Okay, so now I'd like to switch gears a bit and tell you about some more recent work. And to do that, we go back to the Oguri-Vafa geometric construction that we discussed at the beginning. And we're going to change it slightly. So instead of a single brane on L, let me now consider an arbitrary number of branes. And what's going to change is that now not only the theory on S3, but also the theory on L will be given by a non-abelian gauge theory. Now, in the Oguri-Vafa construction, what this means is that after taking the large n limit, one ends up with a relation between open strings, and once again there will be HOMFLY-PT polynomials, but now not only in symmetric, not only colored by symmetric partitions, but by arbitrary partitions. So the question I'd like to study now is how much of the structure that we've uncovered so far continues to hold in this more general setting. In particular, is it still true that the HOMFLY-PT polynomials are encoded by Quiver or by some generalization of that? And what becomes of the basic disks and of the way that they interact? And what replaces the quantum curve, the recursion relation? Is there a recursion relation when you have not just symmetric partitions, but arbitrary partitions? Now, to answer these questions from a physics viewpoint is actually quite challenging. And one technical challenge is that in the case of non-abelian Chern-Simons on L, actually not so much is known about the Hilbert space and the algebra of observables beyond certain special cases. So it's a very subtle question to quantize Chern-Simons theory with a complex gauge group, especially when it's non-abelian. So we're not going to take that route. What we're going to do is we're going to make some working assumptions, which will be well motivated and supported by some checks. So there's two assumptions we're going to make. The first one is that when we take the theory on the brane, the non-abelian complex Chern-Simons theory, we can identify the Hilbert space of that theory associated to the boundary with the HOMFLY-PT skein module of the solid torus. So what that means is that we're going to consider a module that's generated by lines in the Lagrangian. The Lagrangian is always a solid torus. And such a collection of lines, modulo equivalence relations given by the HOMFLY-PT skein relation, they will define the states in our Hilbert space. Now, the skein module of the solid torus has been studied in great detail by Morton and collaborators, and it's known that there's a useful basis for this skein that's labeled by a pair of partitions, lambda mu bar, which as a physicist you can think of as an infinite rank analog of the Verlinde basis, familiar in Chern-Simons theory. The second assumption is about the algebra of observables. So we're going to identify the algebra of Wilson lines with the skein algebra of the boundary torus. And what that means is that we're going to consider an algebra generated by operators, Pij, corresponding to Wilson lines, or line operators, on a thickened torus. And these Pij's, for example, 1, 0 corresponds to the meridian, 0, 1 to the longitude, and they satisfy some commutation relations which are given here. And the way that this algebra acts on the skein of the solid torus is by stacking the thickened torus on the outside. And once again, this has been studied in great detail by Morton and collaborators, and what they've shown is that, well, they computed the explicit action of these operators on the Verlinde basis. So everything is known and we can compute. And then what we would like to do is we'd like to now go back to our setup, and given a not conormal Lagrangian with many branes on top, we're going to identify the quantum state of that Lagrangian with a state in the skein of the solid torus where the coefficients in the Verlinde basis are given by the HOMFLY-PT polynomials. Okay? So these are known. It's something that we can compute by some other means. And so we can compute what is the quantum state of the Lagrangian. Now, what we'd like to do is we'd like to study the structure of this state, whether it's described by a quiver, and whether it admits some recursion identities. So, the first thing that you can try and do is you can try to take what you know about the U1 story, so the A hat operator, and you try to lift it in a natural way. So X would lift to P01, the longitude, and Y would lift to P10. And in fact, this works in simple examples. So for instance, when you have just a single disk, in the U1 case, the open string partition function is this Q-pochamer, and the recursion relation is 1 minus y minus x, as we've seen earlier. And indeed, if you go to arbitrarily many branes, the Q-pochamer is replaced by this expression, which is indeed annihilated by this triple of operators that are the lifts to the skein of 1 minus y minus x. So things work out very, very easily in this example, but unfortunately not in general. Okay? So this is very difficult in general because you have some ambiguities in the U1 case. When you write down A hat, you can trade x and y at the cost of a q, but there's no q in the skein, so you cannot do that. It matters whether you pick an ordering or the other ordering. It's going to be quite different. And another type of ambiguity that comes up a lot is that you can left multiply A hat by any power of x and y. And it turns out that if you do this in the skein, then the operator changes quite a bit. It's not just multiplication from the left. So things are much, much more rigid. And in general, it's not so easy to find relations like this one. This is very simple. It looks exactly like the U1 relation, but in general, it's not going to be like that. So you need a new idea for computing this thing. And what we've done is we resorted to a branch of symplectic geometry known as knot contact homology. So I'll try to very briefly say what are the main points of this construction. So the idea is that we're working now in the result conifold with the Lagrangian brane, and we want to study this from the viewpoint of the boundary. And near the boundary, the result conifold looks like a cone over a contact manifold Y, and the Lagrangian looks like a cone over a Legendrian torus, lambda. And then you can study holomorphic curves or worldsheet instantons that have boundaries that run to infinity. So if a worldsheet runs to infinity, the fact that it's holomorphic implies that it must asymptote to a flow line of the Reeb vector field. That's just because the complex structure pairs the Reeb vector field with the radial direction. So you end up counting some worldsheets that have punctures along Reeb chords like this. And physically that makes sense because these Reeb chords are nothing but the critical points of the action function. In other words, they're the classical vacua for the strings at infinity. So what that means is that you can use Reeb chords to write down what is the space of classical vacua for the open strings at infinity, and it's going to be a graded vector space graded by the Reeb chords on which strings end. But then, in physics, this classical vacua will be destabilized by instanton effects. So you can have strings that are suspended among different Reeb chords, and this destabilizes the space of vacua. So I'm going very fast. This is a whole branch of symplectic geometry. But what's been shown is that one can use these instantons to define a differential that's nilpotent that takes Reeb chords to linear combinations of Reeb chords. And since the differential is nilpotent, one can compute its homology. And we take that as the definition of the ground states of these strings. So to give you an example, the most simple one is, once again, this case with 3 holomorphic disks, also known as toric brane in C3. So in this case, this square represents the boundary torus of the Lagrangian. There is a unique Reb chord with endpoints C plus and C minus on the Legendrian torus. And these blue lines represent the three holomorphic disks that asymptote to that Reb chord. So these are the disks, and what you can do is you can cap them off by using the inverse of path P00. If you do that, you get the three operators that we've seen annihilate the partition function. And the reason why that is the case is that the way we compute this operator is by capping off the boundary of C. So that's a trivial element in cohomology. And so the space of string vacuum, by definition, will be the skein module defined by taking a quotient of the skein algebra by this triple of operators. And in this context, then, we can think of the Chern-Simons state, the quantum state of the brane, as a homomorphism from the cohomology to the skein of L, which maps this trivial element in cohomology to 0. So that's a statement of the recursion relation. So this relation here is a lift to the skein of the U1 quantum curve. But this example is very simple. I told you that we could have obtained this by just naively lifting the U1 story. And in fact, this only illustrates some of the basic properties. More generally, things get a bit more involved, as we're going to see in a moment. And the upshot is that, in general, what you have to do is you have to be a little bit careful when you compute this space of quantum ground states, because it's not always the case that you can just cap off curves and you get operators. Sometimes you have, as we're going to see, you have contributions which have some additional punctures that you have to get rid of. And so you have to do some process of elimination theory. And the upshot is that although we study an example where things work out, it's not obvious. It's not clear in general if this is going to work out. But let's look at one example that does work out. So the Hopf-Link. So the Hopf-Link is uplifted into the Oguri-Waffe setting as two Lagrangians in the result conival, shown here. And so the Hilbert space is then the tensor product of the Hilbert spaces on the two boundary tori, and the partition function, or the quantum state of the brane, is given by the HOMFLY polynomials. So now, let's say we want to compute the recursion relation in the skein for the Hopf-Link. So what we have to do is we have to look at infinity. We have two boundary tori, shown here. And then we have a collection of Reb chords, actually. One is to sit down and compute the differential for the complex generated by the Reb chords. And for instance, if you take the chord that goes from brane 1 to 1, what you find is 4 disks with positive punctures, but then there's a disk that has a positive puncture but 2 negative ones. And so you see that if you just take this, like we did before, and you cap off these 4 disks, you can cap off this one, but you're left with something negative, and you don't get an operator. So what you have to do is you have to study another Reb chord. On brane 2, for example, you find that there's again 4 disks and another disk with 3 punctures. And the idea is that now, with an appropriate choice of capping paths, you may be able to do some elimination theory. So you take these 2 contributions that you want to get rid of, and you cap off, say, the first one with gamma 1, such that it matches beta 2, like we did here. And you cap off the second one so as to match alpha 2. If you do that, you can take the difference of those 2 contributions, and you get some well-defined operator in the skein algebra of the boundary tori. So indeed, you can check that the operator obtained in this way does annihilate the partition function of the Hopf-Link, where you sum over all partitions. And in a similar way, one can show that there's 2 more operators that arise by studying the knot contact homology of the Hopf. And we claim that these three operators completely determine the generating series of HOMFLY-PT polynomials colored by arbitrary partitions for the Hopf link. Now, one last thing I would like to say about this example is, what about the Quiver picture? So I won't have time to say much, but the claim is that if you take the generating series of HOMFLY polynomials colored by arbitrary partitions, then it turns out that you can write it down in a sort of Quiver form, where now the basic objects will be once again holomorphic curves that live in the resolved conifold and have boundaries on the two Lagrangians. And in this case, there will be two disks on the first Lagrangian, like in the unknot. So there's two disks and two disks on the second Lagrangian. But then, in addition, there are two annuli. And the annuli, you see that one of them doesn't link with the disks. It just links with the other annulus. And the other annulus links with everybody else. So it's this one. And it does so on both branes. Now, the point is that these curves, they have boundaries in the skein of the solid torus that give rise to some line operators that are elements of the skein. So there's an algebra on the skein module itself that you can use to make sense of products of these operators. So here these psi's are the generalization to the skein of the Pochhammer. So these are the contributions from the disks on brane 1, the disks on brane 2, an anti-annulus and an annulus, and the star products, they denote some linking numbers. And the claim is that you can write down the whole partition function of HOMFLY-PT polynomials with arbitrary partitions in this very compact form. So this is a Quiver picture. It's generalized to the skein, and it's also generalized in the sense that it includes annuli, not only disks. Okay, so let me try and recap what I told you so far. So Quivers appear to reorganize the open string partition function into finitely many basic curves with linking boundaries. And in the case of knots, these curves are disks. In the case of links, there will be disks, annuli, and maybe curves with more punctures, we don't know. And then interactions among these boundaries generate the entire spectrum of topological strings, or of M2 branes. There is a phenomenon called the multiple cover skein relations for M2 branes. It's a kind of pentagon identity, as we've seen, that relates different descriptions of the brane corresponding to quivers with different number of nodes. Now, when you consider multiple branes on the Lagrangian, according to Guribafa, open strings compute knot invariants colored by arbitrary partitions, and it's conjectured that, at least in some cases is known, and more generally conjectured that quantum curves familiar from the U1 setting should lift to skein-valued recursion operators. And for the case of the Hopf link, we've obtained a complete characterization of these skein-valued recursion operators, so the generators of the ideal for the skein-D module. And we've shown that these compute the HOMFLY-PT polynomials with arbitrary partitions. And finally, we also find that the Quiver structure continues to hold, in the case of the Hopf, to a Quiver valued in the skein. So I'll stop here.
Questions? So,
So,
What exactly are the skein valid quivers? Is it just something that encodes the linking of the boundaries of the basic curves, or does it encode some more information?
Yeah, that's right. So the idea of a skein-valid quiver is that so it's still true that you can write down, first of all, some basic building blocks. So the basic building block, let's talk about knots, right? So knot links. The basic building block in that case would be a disk, and the disk is something like the partition function of toric brane in C3. Okay, you can write it down. So it's something like lambda product box in lambda q to the minus the content of the box, q to the hook length, q to the minus the hook length, times w lambda empty. And so this would be, say, what I call psi of this. And then, so once you have this kind of building block, then, well, of course you can dress it up, right? You can put some variable psi here that comes here as a sort of homology counting variable, psi to the number of boxes in lambda. So think of area coming from wrapping the P1. This psi could be a square if you have a disk that wraps the P1 in the conical. Okay. Anyway, so you can have these basic disks like in usual U1 quivers. And then you're asking how do you put them together, right? And what's a bit non-trivial, at least from the viewpoint of the skein, but it seems to hold, is that what you can do is you can write down the partition function by using the algebra of this operator. So I told you there's an algebra, there's this skein torus algebra that acts on the skein module, but there's also an algebra on the skein module itself. All right, so W lambda, W mu is given by the Littlewood-Richardson coefficients. And there's a generalization of that to the case where also the second partition is non-empty. So there's something called universal character algebra. And what you do is when so if you have two disks that do not link, you just take two of these and you take the product of them using this. If they do link, you can introduce a linking factor. So this is the star product that I defined. And the definition of the star product is that W lambda star F W mu will be something like sum C lambda mu nu Q to the kappa of, F kappa of mu minus kappa lambda minus kappa mu times W mu. So this kappa of a partition is defined as the sum of the mu I square minus sum of mu transpose I square. And so it's a function of the partition that comes up when you do a change of framing. Okay. So one way you can think about the star product is that you sort of take two disks next to each other. You change framing a certain number of times so that you link them f times. And then these subtractions undo the framing on the single strands. So what you're left with is the original strands linking f times without being framed themselves. So yes, this is how the linking works. Does that answer your question? Maybe.
Other questions?
Do we need M5 brane such that the M2 brane may not understand M5?
Sorry, say it again.
Do we need M5 brane for this M2 brane? M2 brane have boundary.
So the question is whether you need an M5 brane. Yes, you need an M5 brane because otherwise you wouldn't have open M2 branes.
Yeah, so what is M5 brane?
Oh, the M5.
Yeah.
Yeah, so we talk about M5 when we leave to M theory, and in that context, after the transition, there's M5 that wraps the conormal Lagrangian times S1 times R2. So we do M theory on the result conical times S1 times R4.
Yeah, but this Lagrangian M5 is it doesn't have topology. And use this type this M2 could link to each other. They have linking number, but this M5 doesn't have this geometric structure. So how could it be possible that M2 could link to each other?
I didn't understand the question, so okay.
So in your talk you discuss this M2, they have boundary, and this boundary could link to each other.
Yes.
And you get this quiver, right?
Yes. Yes.
And this linking number should be some geometric structure of this M2 group, right?
Well, but the linking happens inside L.
Yeah. There should be such a link. This such that the M2 group could end on this link.
Yeah.
Yeah, and this link should be some geometric structure. This M5 point, right?
It's inside the M5 brane. Yes.
Yeah. Then what's this M5 point looks like?
Oh, the M5 is the whole Lagrangian.
So
Right.
this is Lagrangian, and you said it's S1 cross R2, so its topology is trivial.
I don't know. Maybe we should discuss more in detail after the talk, because I'm not sure I understand the question.
Yeah.
Yeah.
So this skein quivers, are they an analog of this LMOV and DT invariance?
Well, actually, the LMOV, as we've seen in the previous talk, they're defined for high rank as well, right? So the LMOV are just defined for arbitrary rank. For the DT, yeah, I'm not sure. That's a good question.
Yeah. And what is the combinatoric problem for these skein quivers? Because
The
for
combinatoric-
regular quiver, we have this combinatoric problem of invariants of maps.
What?
Combinatoric problem associated to that.
To
the skein
the
quiver.
skein value quiver. So what kind of combinatorics do you have in mind for the usual quiver?
For generic motivic series, we have the invariants of map, number of the maps in the quiver representation theory.
Yeah. Well, so the skein value quiver is again counting just maps, right? So when you write down the skein value quiver or the skein value partition function, it's just a generic number of branes partition function. You can always specialize. So if you truncate the sum of all partitions to partitions with up to a certain number of rows, right? Then you go back to having fixed number of branes in the Lagrangian. So then it's just a regular open string partition function. So it's
Is
just
that related to the higher rank DT theory?
So when people talk about higher rank DT theory and Calabi-Yau, usually they mean that they have a certain number of D6 branes that wraps the whole Calabi-Yau. No, I don't see a relation. Yeah. It's a very different setting. Maybe. Thanks.
Any other questions? Well, let's thank Pietro again.